Hi everyone, I'm GOZDE Damla TURHAN. I am going to present our paper today with GUZDEN, VARINLIOGLU, MURAT, BENGISU from IZMIR University of Economics, Turkey. So the main purpose of this research was to develop a load-bearing composite material out of bacterial cellulose and to integrate the mechanical test results to digital optimization processes. Actually, there are many studies on bacterial cellulose found in the literature, such as the products of fashion design, packaging, or acoustics, etc. But our motivation is to design composites that perform as a load-bearing component. And the process is like the synthesis of methods and tools from multiple disciplines, from biology, material science to digital architectural design and fabrication. So the process started with different recipes, with different ingredients and observations on how it formed cultures on itself and behavior under tensile forces. There wasn't any reaction to compressive forces because it has a very rubbery and opaque materiality and it is elastic. Each of the ingredients provided a slightly different stiffness and elasticity, but we followed the common recipe to start with and in order to be able to compare the results in the literature. So for the reinforcements, we investigated different types of fabrics, but the criteria was being a cellulose-based fabric, plus it would be expensive, time-consuming, or not animal-friendly. We, for instance, employ silk or bamboo. So jute seemed to be the most accessible cellulose-based fabric. And we were also searching about the form, and we came across with GOZDE's catenaries. He was using the catenary geometries as a form-finding method. He first hung the cables from the ceiling and then put a mirror underneath it to figure out the ideal form. So that was the originating point of the form that we used in this research. So we studied on how to replicate GOZDE's method in a digital platform, and we got more into dynamic relaxation in digital optimization processes. These processes are usually used for cable and fabric structures, tensile structures, or membranes, which was a perfect fit for us. The aim was to find the geometry where all forces are in equilibrium, just like GOZDE did. So I will talk a little bit about the growth process and then move to the experiments. We use the common recipe, as I said, to grow the bacteria with those ingredients and in certain growth conditions. In order to test bacterial cellulose and composite, we use the texture analyzer with mini-tensile grip probe. So we can get quantitative data regarding the tests with the mini-tensile grips probe. It provides us the values for force, distance, time, strength, strain, and we can also derive stress, Young's modulus, and elongation at break values. So we conducted the tensile test for two samples, pure biofilm and the bacterial cellulose jute composite. This is the tensile test for sample 1, the pure biofilm, and this is the force time graph for sample 1. The red line shows that the sample got completely deformed, broken at the 5th second of the test. The test speed was 2.5 millimeters per sec, and the strain was found to be 2% for the pure biofilm. And we conducted the test for sample 2 here. The jute here has a basic weaving pattern. They grew together with bacteria. And you see the graph for the sample 2 here. It was not deterministic. I mean, it did stretch, but I think it inclined to be more stiff. After the tensile tests, we look for an integration into a digital platform and saw that we actually can integrate those data into Kangaroo. These are the components that we can allocate values coming from the tensile testing. In order to simulate the point that the yield strength is exceeded at, we introduced the equation. By reusing the modulus of elasticity equation, another calculation is expressed in order to compare the ratio of force to maximum force for validating the simulation. If the ratio is among 0 to 1, then it indicates that the connection is in elastic behavior, so the simulation is correct. If this value is higher than 1, then the material is in plastic behavior, so the simulation is incorrect. Our results show that the composite sample has displayed a higher tensile strength in mechanical tests compared to the pure biofilm due to the reinforcement of its three-dimensional network structure, although tests should be repeated several times more for validation. By incorporating the tools shown earlier in the paper, Kangaroo ran for pure and composite biofilms, resulting in a value between 0 to 1, which indicates an elastic behavior, so the simulation is correct. It was seen that the mechanical and digital testing of such biologically active materials together leads to an integrated structural optimization with high level of accuracy. We are also currently working on other composites with different fabrics with different gaps between the threads. And we envision that such process might also result in a customized plugin for a large number of customized biodegradable design prototypes within the context of form finding of complex geometries for real life design applications. So thanks for listening.